want to continue our exploration of proofs, we're going to take a look at one part of the extended linearity principle as it applies to systems. Now, in our textbook, we looked at first-order equations and second-order equations, and we had there both the linearity and the extended linearity principle. For systems, the book only actually introduced the linearity principle. So here, I'm going to look at the extended linearity principle as it applies to systems, and this is a little bit new. Okay. Here's what I will promise on the final exam. I've told you there will be a proof. It could involve the linearity or the extended linearity principle, but I won't give you this particular combination of the extended linearity principle as it applies to a system. However, I'm going to go ahead and use that as my example for this video, partly because I think it's important that you recognize that it doesn't really make that much difference whether you're working with a single differential equation or a system of equations, and whether the differential equation is first order or second order. The concepts behind the linearity and the extended linearity principle are the same. And the context in which you see that doesn't affect the underlying context. So if you can look at this problem more as what's similar about it to what you've seen before than what's new, then you're really grasping that connection. Okay, so we're going to let A be a real-valued 2x2 matrix. Now, what we're used to working with is equations that look something like this. Y prime, where y, of course, would just be x of t, y of t. So it's a pair of real-valued functions. Y prime is our matrix times y. Okay. Now, that's a linear system. It's also homogeneous. Okay. Notice, if I were to move this over to the other side, I would get y prime minus a times y equals 0. So just like the homogeneous equations that we see when we have a single equation, if I put all the stuff that involves y or y prime or any of its derivatives on one side, I get 0 on the other. Okay, so there's no function of t just hanging out by itself. Okay. Now, that's what we worked with in Chapter 3. Here's what I'm introducing that's a little bit new. I'm going to let v be a vector consisting of two real-valued functions of t, f of t and g of t. Okay. So this is like a vector function of t. Now, if I have y prime equals ay plus v, that's now linear but not homogeneous. Okay. If you change these from being vectors to just being, whoops, that's a vector function. Change these from being vectors to real-valued functions, this would just be a non-homogeneous linear differential equation with a constant coefficient. Okay. Okay, so I want to take a look at that. And so basically, this would be the associated homogeneous equation that's associated with this. This sort of system might arise if I had a forced harmonic oscillator. So we definitely studied those. We just studied those as single differential equations. But we know that single differential equations correspond to systems. So a forced harmonic oscillator, that second-order differential equation, could easily be written as a non-homogeneous linear system of differential equations. Okay, so the extended linearity principle basically says if you have a solution to the non-homogeneous equation and you have another solution to the associated homogeneous equation, then if you add those solutions together, you've built yourself another solution to the original non-homogeneous equation. Okay, so that's what I want to try to prove. Okay. Now, if you want to, when you're working with vector equations, you can write things out component-wise. It's not necessary to do that, so I'm not going to. If you do choose to write things out component-wise, remember that if you're introducing this notation, you need to define it and formally introduce it. You can't just start writing this in place of y. You need to say, let x of t, y of t be the components of y, so that y is this. Okay. All right, so I'm going to take these two equations as given. That's all I'm taking as given, and I'm going to prove the extended linearity principle. Okay. So there's an if part. My job is always to suppose the if part. Okay, so I'm going to just keep the problem up there. Let's suppose that y1 is a solution, to double star, the non-homogeneous equation. And I'm going to spell out what that means. Then I know that y1 prime is equal to a times y1 plus v. Let's call that, I'm going to actually call that monster, just so the double face goes with the double star. Okay, so, and we'll also suppose the other part. Suppose that y2 is a solution to star, which would be the associated homogeneous equation, and I know what that means. Then y2 prime is equal to a times y. Okay. So I've supposed the if, and I've spelled out what it means. Oh, let's call that smiley face, because I'm going to need to refer back to that. Okay. So then I need to prove the then part. I find it helpful to just write down claim and state the then part so that I've got the thing that I'm trying to prove. So I'm claiming that y1 plus y2 is a solution to double star. And just like with my suppositions, I want to spell out what that means. Okay. So at this point, I'm going to erase the statement of the problem. And actually, just to clear some space, I'm going to erase this too. Let me just recopy real quickly what star and double star were. So I'll recopy those up at the top. So star was the associated homogeneous, that y prime equals ay, and double star was the non-homogeneous, y prime equals ay plus v. Okay, so I'm going to just spell out now what my claim is. My claim is that y1 plus y2 is a solution to this, which means if I replace the y's here with y1 plus y2, that's what I'll get a true equation. So y1 plus y2 prime is equal to a times y1 plus y2 plus v. That is my claim as an equation. So I'm not at this point saying that that is true. I'm saying I'm about to prove that. Okay. So this is an equation that has two sides. It has a left-hand side and it has a right-hand side. So let's just simplify each side. So the left-hand side is y1 plus y2 prime, or the derivative of that. Well, that's y1 prime plus y2 prime. And that's just the sum rule of derivatives. Okay, let's do the right-hand side. The right-hand side is a times y1 plus y2 plus v, and that's equal to a times y1 plus a times y2 plus v. Okay. So that's just using the fact that matrices distribute over vectors. Matrix multiplication distributes over vector sums. Okay. Excellent. But now I can say, hey, a times y2 is the same thing as y2 prime, and a times y1 plus v is the same as y1 prime. So I think I maybe want to switch the order of those two things so that I'm putting a times y1 next to v, because they add up together to give me y1 prime. So actually, let's switch the order of these two. Let's see. So that's equal to ay1 plus v plus ay2. That's me just using the commutative law of vector addition, that the order doesn't matter. Again, in your proofs, if you want to explicitly write out the reasons, you're certainly welcome to do that. In the interest of space in these videos, I'm simply saying the reasons. My requirement, though, is that you do one step at a time. Don't combine steps. Okay. Okay, but now I can say, oh, well, this is just y1 prime, and this is just y2 prime, and that's by monster and smiley face. That's by me spelling out my suppositions earlier. But that was exactly what I simplified the left-hand side to. So thus, the left-hand side is equal to the right-hand side. The claim holds. Now you'll notice I was dealing with vector functions here. However, if I hadn't been dealing with vectors, the only difference would be that I wouldn't have these bars over things. So the extended linearity principle would be very, very similar if I were just dealing with a first-order equation or a second-order equation. In this case, I had the coefficient in front of my term that wasn't the derivative was constant, because it was a matrix consisting of constants. In the previous example, we had that our coefficient functions were actually functions of t. So there are lots of different variations that we can have, but the gist of these things is basically the same. It all hinges on what does it mean to be a solution. It means when you plug in that function and its derivatives, you get a true equation.